Okay, so in this part of the lecture, we're going to see examples of diffusion maps, of actual graphs. And so we'll start with just perhaps the simplest graph, right? So we just take a cycle on n nodes, right? So just think of, I mean, we can draw it here, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So we have a cycle on 10 nodes, and now we can ask, what is the easiest way to, what's the most natural way of drawing this cycle in this graph in 2 dimensions? Of course, the most natural way of drawing this is exactly, right, what is drawn here. So this is diffusion maps for the 10 cycle, and you see that it does exactly what would be natural, right? And in this case, it's actually not so hard to prove, because if you think about the cycle, it's if you number the nodes as node 1, 2, 3, 4, 5, 6, and so on, then this matrix is circular. So it's diagonalizable by the Fourier transform, the discrete Fourier transform. And so the leading eigenvectors you'll see will just be some cosines and sines, which is exactly the x and y coordinates of this, right? So it's inscribed in a circle, and you see exactly the most natural representation possible of a cycle. Now let's make things a little more interesting, right? And let's say that what we do is I'm gonna create data that comes from a game of Pac-Man, right? So a very strange game of Pac-Man. Okay, so let's do that. Let me zoom in a bit more. Okay, and so what we'll do is we'll take a data set that comes from a game of, like an arcade game of Pac-Man in a very special way. So we take pictures, right? And in these pictures, there'll be a yellow blob. Think of it as Pac-Man, right? But just some yellow blob in the picture. And there's nothing else. There's no paths. There's no other things to eat or to be eaten by or anything like this. Now what I do is I take many of these images, right? Maybe Pac-Man is here, and so on with Pac-Man always the same, and I take a data set made of, say, a few thousand of these images, right? Sometimes it's one position, other position, and so on. And let me start by making them in 1D. So what I mean by this is Pac-Man is actually only allowed to go to the right or to the left, right? But perhaps importantly, if it's showing up, if it goes on one side, like if you played an arcade game, right, when it goes here, it shows up on this side. Let's see if I can draw. Right, so when it comes here, it shows up on the other side. Right, and so now I draw lots and lots of, right, I'm going to draw on the computer lots and lots of images with Pac-Man in a random position in exactly that, right, in precisely this type of data. I just make, this all say black and this yellow, and I draw at random the position of Pac-Man, but it can only go left and right. And now I grab that data set, right? This is now a manifold. This is potentially in very high dimensions, because say, if we have something like, maybe 20 by 20 pixels, which is actually quite little, right? Of course, pictures have much more than that. We're already in 400 dimensions. But if we think about how to parameterize this object, right, this is really a one-dimensional object, because Pac-Man can only go left or right, right? You can completely capture the image by just one parameter, which is the position of Pac-Man in the x-axis, right? And so we can ask ourselves, can we learn what this manifold is? Can we learn the geometry of this data? And of course, if you think about it, this data is just a circle, right? I mean, this is completely described like a circle, right? Because if I just go right, I just keep going back and forth, right? Just like a circle. And so now we can see what happens if we try to build a graph with using some kind of kernel out of this data set of images. And you see that what you get is exactly a circle, right? So you get something that looks like this, as you can see in this image here being shared. Okay, now let's make things more interesting, right? Let's make things have, let's make it go in both dimensions now. Okay, so a bit closer to the true game, where now Pac-Man is allowed not only to go left and right, but up and down. Right, so I might see it like this, right? I might see it, let's see, right? I might see it maybe, right? Like, again, the same thing happens on this side, right? If it shows up on one end, it will appear on the other from the top. And now I take many, many images, let's say like 10,000 of these pictures. Right now, of course, I mean, I do it on the computer without having to actually draw Pac-Man or anything like this. I just take a bunch of images like this. So here's an example of the data set. Here I just took, this is a few of them, right? I took a lot more. And I just made a random assignment for the position of the yellow blob. Right? So the yellow blob is picked at random. It can go left and right, up and down. And when it goes in one A, it shows up on the other. Now, the question is, what is the geometry of this data set? Again, this is some weird manifold in dimension. Now, in this case, 400, because we actually, in this case, just have 20 pixels by 20 pixels. And now we ask, what is the geometry of this? Now, if you think about, say, this being like a map of Earth or something, right? Or I should say, most when asked this question, of course, in the recording, it's hard to get an answer because there's no one on the other side. But when I ask this question, usually the first answer I get is that it's a sphere, right? We're all used to seeing maps of Earth like this, and we all know, right, for a few hundred years now, that if we go on one end, we show up on the other in the map. However, it is not true that if you go to the North Pole, you'll show up in Antarctica, right? The geometry of the sphere is not this. In particular, right, if you think about what this geometry is like, right, it's this goes and rolls, right? This part meets that one, so it rolls like this, and then this one meets that. So it rolls this way. So this is what we call a torus, or a donut, right? The geometry of this is a donut. You roll this way, and then you roll the other way, and it's just a donut. So now we can ask, can diffusion maps see the donut when I do it, when we ask diffusion maps to draw this in 3 dimensions, right? If we draw it in 2, it would be hard to see the donut, but we can see the donut in 3 dimensions, right? I just sort of embedded here the donut in 3 dimensions, right? There's this thing, you may have seen this, that this Klein bottle cannot be embedded in 3 dimensions. The Klein bottle is a different thing, right? It's like, it's essentially the same thing, but if Pac-Man, when he goes here, shows up here with inverted, right? So it's like, if I was to do a Mobius strip and then try to roll it like I'm rolling the torus. And that we can do in 3 dimensions, but the torus we can't. And so let's see what diffusion maps gives. And it gives exactly a torus, right? So this is what diffusion maps gave us as the visualization of this graph, which was obtained by just taking many instances of the game of Pac-Man, right? This very simplified game of Pac-Man, and asking it, try to learn from me what is the geometry of this set. And you see that, it learns exactly the torus, right? It has a donut exactly. There's this sort of side, there's a middle hole in there for the torus. It really learned that the right geometry for this is the donut, right? Which is, I think, quite impressive. And if you think about, like, why is it, how is it learning these things, and what's a good example to think about? And a very nice example is the Swiss roll. So the Swiss roll is like, you can think of it as a data set like this, right? And now you think, okay, what is the geometry of this, right? The geometry of this, right? Let's say nothing is touching, right? It doesn't matter that it's curved in space. The geometry should just be the geometry, right, of this plane, of this strip. Right? But when it's like this in Euclidean space, the geometry is a bit different because these 2 points are way too close in the ambient space than their real geometry. They're much further away, right? If I take a point here, right? If I take a point here and a point there, if I have an ant going around, it would have to go over the whole thing. But in ambient space, they're potentially much closer, right? Because this point and this point could be a lot closer. And so this is exactly one of the intuitions behind diffusion maps, is you want to learn the geometry independently of how you're embedded in ambient space. And so you can always sort of trust small distances, because if 2 points are extremely close, even in ambient space, they will be close. What you cannot trust is sort of middle range distances or large distances. And so with these kernels that we saw, like the Gaussian kernel and so on, it does exactly that. And so you would consider the distance now, after it embed, you would take the distance between these 2 points to be some kind of diffusion. Like if I diffuse heat, how long does it take to get there? Or if I diffuse some chemical or a random walk, and the heat needs to go around, right? Because it won't have something to propagate here, right? The random walk will have a very low probability of jumping because this is of a scale higher than that epsilon. And the Swiss roll is a nice example. And now, just to show you some more sort of realistic examples, these are not done with diffusion maps, but it's sort of essentially the same thing. It's done with isomap, which is a little different. It starts by looking at geodesic distances and then embedding those in a certain way, but in these examples, they work very similarly. And in this paper, where they use and develop ISOMAP has some very nice pictures that I want to show you. So this is a paper by Tenenbaum, De Silva, and Langford in Science in 2000. This is a reference in the lecture notes. And here, first it starts with, the first example will be pictures of a face, right, of say a statue, and with different lighting conditions, right, or different viewing of the angles or poses. I mean, I can either move my face or move the camera. This is, of course, the same thing. And now if you look at this data set, and we do diffusion network, in this case with ISOMAP, but it's a very similar idea, then if we do it, we see that the 2 dimensions that it learns are actually very interpretable, right? One, the up-down is just actually here, the way it was described, is just up-down pose, and you can see in these images. And left-right is actually just left-right pose. So it's learning the geometry of this set, not by all the pixels of the face, but actually learning the parameters of the movement of the face, right? That's really impressive. You can do the same thing with pictures of hands and wrist and a hand that's open and closed and rotates, and it learns exactly these 2 dimensions. You can do it with pictures of numbers, and you see that it's possible to interpret these 2 dimensions. So one thing that I recommend is if you get a data set, right? I mean, you can first try PCA, but maybe PCA is not able to see that, right? PCA is very linear. It won't be very good at telling that things are sort of curved, or it will trust large distance and small distance is just the same. And so one thing, if PCA is not working, one thing you should try to do is just try to do diffusion maps, right? You have to pick T, you have to make the walk lazy. Usually it doesn't depend so much on those things, but I usually make the walk a little lazy, and then pick some reasonable T, like 3 or 4, and just visualize the data in 2 or 3 dimensions. Just see what it looks like, what your data looks like, what your graph, or see if you can learn the geometry of your data. Now, I should make a comment that on this very simple Pacman example, because of how I draw a very simple case, actually PCA will work. Sort of for the wrong reasons, but it will work. Because the place where the inner product will be non-zero, if I say think of this as 0 and this 1, is just when you have an overlap. And when you don't have an overlap, the inner product between the 2 images will always be 0. So PCA in this case, for sort of the wrong reasons, is also not trusting long distances, because it's just putting inner product 0 to all of them, right? And so in this case, will also work, but sort of for the wrong reasons. If you try it on a data set with actual, say, game of Pac-Man or something, then diffusion map should do a lot better. Right? Thank you.